Monomials, things like x to the power of n, are the building blocks of polynomials. So let's see if we can figure out how to differentiate these functions. We'll immediately start off with a theorem. If n is any natural number, then the function f of x equals x to the n is differentiable at every real number. The derivative of f is given by n x to the n minus 1. I sometimes think of this as the n leaving the exponent to join the x, leaving one less number in the exponent, whatever mnemonic you use, though this is a critical rule to remember. To throw out some quick examples, the derivative of x to the 7 is 7x to the 6 per the formula above. And even if the exponent is ridiculous, like x to the 2037, the formula for the derivative holds all the same. Now, as I mentioned, knowing how to differentiate monomials will tell us how to differentiate polynomials. That's because all polynomials are sums and scalar multiples of monomials. Since the derivative is linear, we can now differentiate any polynomial. I'll start by showing you how this works abstractly. Let's suppose we have a generic polynomial, like so. To find its derivative, we'll differentiate each of its portions separately. Okay, now I haven't done anything yet, right? I'm just writing this in a nice form. Now I'm going to use linearity to break the polynomial down into its monomial constituents. I'm using both the additive and scalar multiple portions of linearity at the same time here, just to save on some work. Differentiating the terms in the square brackets using our power rule formula gives us the following. Notice that the degree of the polynomial went from being n to now being n minus 1. Differentiation will always lower the degree of the polynomial. Now this work is actually even easier to see in sigma notation. By writing the polynomial in sigma notation, additivity allows me to pass the derivative inside the sum, while scalar multiplication allows me to move the a sub k's to outside of the derivative. Now I'll apply the power rule, giving us our answer. As one final step though, note that when k equals 0, the first term of the sum is itself 0. So we often restart the sum from 1 in order to account for this. Okay, that probably looked like a bunch of abstract nonsense, so let's try to ground this in a concrete example. Let's find the equation of the tangent line to the function f of x equals 2x squared plus 3x minus 7 at the point x equals 1. Now we're going to need a point through which the line passes, with 1 f of 1 being the obvious candidate. It's not too hard to work out that f of 1 is equal to negative 2. The slope is given by the derivative of f at 1. Our conversation above tells us that the derivative of f is 4x plus 3, in which case f prime of 1 is equal to 7. Putting it all together with the point slope formula gives the equation y plus 2 is 7 times x minus 1. Alternatively, in y equals mx plus b form, we would get y is equal to 7x minus 9. Hopefully you're starting to see how by having a collection of tools at our disposal, we're able to take complicated functions and compute their derivatives without too much trouble.